Prepare yourselves for a vast upheaval of exceptional extents. Betelgeuse, the red monster star balanced on the edge of our system, is conveying unfavorable messages through the universe. Utilizing the James Webb Space Telescope, cosmologists have revealed something significantly disrupting about this giant heavenly body. As famous astrophysicist Brian Cox gives a grave admonition, the inquiry looms. Are we on the brink of witnessing a catastrophic cosmic explosion that could forever change the night sky as we know it? Let us dive in. In the grand tapestry of the universe, where stars are born, live, and die in spectacular fashion, one star has recently captured the imagination and concern of astronomers and the public alike. This star is Betelgeuse, a red supergiant of immense proportions and age, located prominently in the constellation Orion. Its distinct reddish tint and variable brightness have long been a source of fascination. However, recent developments have heightened interest in this divine giant. As we explore the nature of Betelgeuse, we find ourselves on the cusp of a potentially monumental event in the life cycle of the star. But what could these changes in Betelgeuse signify? Are we witnessing the prelude to a cosmic spectacle of unimaginable scale? Betelgeuse, roughly 700 times larger than our Sun, is a stellar behemoth. Its epic size is almost beyond human comprehension. Imagine a star so massive that, if it were to replace our Sun, its surface would extend beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars in its celestial embrace. This staggering size not only speaks to Betelgeuse's physical characteristics but also reflects its stage in the stellar life cycle. As a red supergiant, Betelgeuse is in the twilight of its existence, a phase marked by expansion and cooling after a lifetime of fusing hydrogen into helium in its core. But what about the age of Betelgeuse? This star, believed to be around 8 to 8.5 million years old, is relatively young in human terms but ancient in the context of stellar lifetimes. Its current red supergiant phase represents the culmination of millions of years of stellar evolution, a period marked by dramatic changes and processes that transformed it from a hot blue star to the red giant we see today. The life cycle of stars like Betelgeuse is a tale of transformation, driven by the relentless forces of nuclear fusion and gravity. Betelgeuse's distinctive reddish tint is another indication of its current stage. The red color results from its relatively cooler surface temperature compared to other stars, such as our Sun. While the Sun's surface temperature is about 5,500 Kelvin, Betelgeuse's cooler surface registers at around 3,500 Kelvin. This cooler temperature allows Betelgeuse to emit light at wavelengths that give it a red appearance. However, this color is not merely a visual trait. It provides clues about the star's physical state and the processes occurring within its vast gaseous expanse. Adding to Betelgeuse's mystique is its historical color change. Ancient Roman and Chinese texts suggest that nearly 2,000 years ago, Betelgeuse was yellow. It was only in the 9th century that Arabic scholars first described it as red. This color shift over human history is not a trivial detail but a clue to the star's evolutionary path. The variable brightness of Betelgeuse is another fascinating aspect. It is a semi-regular variable star, meaning its light periodically waxes and wanes. This variability is a characteristic dance of luminosity that has captivated astronomers and skywatchers for centuries. Typically, Betelgeuse undergoes a 400-day cycle, along with a longer cycle lasting about 5 years. These cycles were recorded as far back as 1836 by Sir John Herschel and possibly even earlier in indigenous oral traditions. What makes Betelgeuse truly enigmatic, however, is its inconsistency. Unlike many stars that follow predictable patterns, Betelgeuse sporadically deviates from its rhythmic dimming and brightening, hinting at complex and less understood processes occurring within its titanic structure. In late 2019, Betelgeuse captured the attention of cosmologists and stargazers worldwide with a surprising and dramatic change in its appearance, an event now widely known as the Great Dimming. The red supergiant, one of the brightest stars in the night sky and a prominent feature of the Orion constellation, began to mysteriously dim. The dimming was so pronounced that it started losing its brightness at a rate of 0.01 magnitudes per day, reaching its lowest brightness in February 2020. Betelgeuse, normally visible to the naked eye even in light-polluted areas, became extraordinarily faint, a change noticeable even to amateur observers. However, there is one challenge with monitoring Betelgeuse's activities: the time paradox. When we observe a star like Betelgeuse, we are not seeing it as it exists today but as it was in the past, due to the time it takes for light to travel to us. In Betelgeuse's case, at approximately 725 light-years away, the light we see today left the star nearly 7 centuries ago. This delay makes it challenging to predict and monitor sudden changes in a star's behavior, as we are essentially looking into its past. The unfolding of Betelgeuse's celestial drama was closely monitored by Andrea Dupree, Associate Director of the Center for Astrophysics at Harvard and Smithsonian, and her team. They used the Hubble Space Telescope to study the behemoth star as part of a 3-year project to observe variations in Betelgeuse's outer atmosphere. These observations offered unprecedented insights into the dynamics of a variable star like Betelgeuse, which regularly expands and contracts, causing fluctuations in its brightness. Hubble's sensitivity to ultraviolet light allowed researchers to probe the layers above the star's surface, heated partly by the star's turbulent convection cells. Further analysis of Hubble's spectra taken throughout 2019 and 2020 helped measure the movement of material in Betelgeuse's outer atmosphere. Specifically, the spectra focused on magnesium-2 lines, indicative of the star's atmospheric conditions. These observations revealed material moving at speeds of around 200,000 miles per hour from the star's surface into its outer environment. This hot, dense material extended thousands of miles from Betelgeuse and became the precursor to the dust cloud that caused the star's dimming. Dupree and her team estimated that about twice the normal amount of material from Betelgeuse's southern hemisphere was ejected over 3 months during the outburst. This mass loss was significant, especially considering that Betelgeuse, like all stars, continuously loses mass, but at a rate far greater than our Sun. The magnitude of this mass ejection and the subsequent dimming sparked discussions among astronomers about whether this event could be a precursor to a supernova explosion. The proximity of Betelgeuse, about 725 light-years from Earth, adds to the intrigue. Any such explosion would be visible from Earth and provide an unprecedented opportunity to observe a supernova up close. However, the question remains: does this dimming event signal an imminent supernova, or is it merely an extraordinary episode in the star's long and complex life? Several theories were proposed to explain this sudden change. One popular hypothesis suggested a stage in the supernova process, a speculation that gained traction due to the common belief that Betelgeuse is nearing the end of its life. Another prominent theory implicated dust, possibly ejected by the star itself, as the cause of the dimming. Betelgeuse, like other red supergiants, is known to shed material, and this ejected material could form a dust cloud thick enough to obscure the star's light from our perspective. A third explanation considered changes in the star's photosphere, the visible surface layer, which could affect its apparent brightness. In-depth investigation using various observational techniques unraveled this mystery. Spectroscopic analyses indicated a drop in Betelgeuse's effective temperature, suggesting the dimming could result from a massive dark spot on the star's surface. This theory was supported by observations that Betelgeuse's temperature decreased by at least 170 Kelvin during the dimming, pointing to significant changes on its surface. Ultimately, the key to understanding this strange phenomenon came from humanity's sentinel in space: the Hubble Space Telescope. Hubble's observations revealed that Betelgeuse's dimming was indeed caused by a massive ejection of hot material into space. This material formed a dust cloud that obscured part of the star's surface, effectively reducing the amount of light reaching Earth. The dust cloud likely originated from extremely hot plasma, which erupted from a large convection cell on the star's surface and moved through its warm atmosphere to the cooler outer layers. As it cooled, it formed dust grains, creating a cloud that blocked light from about a quarter of the star's surface. Hubble's ultraviolet spectroscopic observations, which began in January 2019, were crucial in piecing together the timeline leading up to Betelgeuse's dimming. These observations captured signs of dense, heated material moving through the star's atmosphere in the months before the dimming. In December 2019, several ground-based telescopes also observed the star dimming in brightness, particularly in its southern hemisphere. This material, initially more luminous than the star's typical brightness, eventually led to the formation of a dark cloud as it moved outward. While the event provided valuable insights into the dynamics of massive stars, it also left astronomers with more questions about Betelgeuse's future. Could this be the beginning of its final chapter? Or is it merely a dramatic episode in the life of a red supergiant? Betelgeuse's story is far from over, and its fate remains one of the most captivating mysteries in the cosmos. Proposing a more fierce and conceivably unusual end-of-life stage for these stars, might Betelgeuse gear up for its grand finale, a cosmic explosion blast, within the next couple of centuries? Ongoing studies hypothesize about the timing of such an event, suggesting it might be sooner than previously thought, possibly in just a few decades. The concept of bow shock is another critical piece of the Betelgeuse puzzle. As this epic star rushes through space at approximately 67,000 miles per hour relative to its surrounding interstellar medium, it creates a bow shock much like the one formed by the bow of a moving boat. This phenomenon occurs as the star's outer layers interact with interstellar gases and dust, providing a spectacular demonstration of the star's dynamic nature and its interaction with the cosmic environment. Studying this bow shock not only informs us about Betelgeuse's current state, but also contributes to our understanding of stellar evolution and mass loss processes. But what about the star's recent behavior? Betelgeuse's surface has been observed to cool and become less dense following the ejection event, leaving the star in an unstable state even years later. Hydrodynamic simulations suggest a connection between the star's convective activities, the mass ejection, and subsequent pulsation mode switching. This ongoing instability raises questions about the internal processes driving these changes and how they might culminate in the future. Additionally, the mass loss rate of Betelgeuse, as observed, is significantly higher than that of many other stars, indicating a complex interplay of internal forces. The persistent pulsation, partially responsible for this mass loss, is constrained by the continuous energy dissipation through shock heating and mass ejection. These observations highlight the dynamic and somewhat unpredictable nature of Betelgeuse's life cycle, prompting astronomers to reassess their models of stellar evolution. However, one might wonder, with all these dramatic changes, is Betelgeuse nearing the brink of going supernova? The question looms large in the astronomical community. While the timing of such an event remains uncertain, the recent massive ejection has undoubtedly shifted the discussion, hinting at a more imminent end than previously expected. Theories now grapple with the implications of such extensive material loss and what it means for the star's stability and future. As the astronomical community eagerly watches Betelgeuse, another cosmic event captures attention: the supernova SN 2023 ISF. This spectacular explosion occurred in the galaxy Messier 101, colloquially known as the Pinwheel Galaxy, located a mere 21 million light-years away. Discovered in May 2023, SN 2023 SF isn't just another supernova. It is the closest one observed in recent times, offering a priceless close-up of a star's catastrophic finale. The discovery of SN 2023 ISF was nothing short of a cosmic coup. Koichi Itagaki, a renowned amateur astronomer known for his supernova discoveries, first spotted this rapidly brightening point on the outskirts of Messier 101 using a modest 0.35-meter telescope. Once he announced his find, the astronomical community sprang into action. Observatories worldwide, from Earth's surface to the orbiting Hubble Space Telescope, pivoted to capture the unfolding drama of this nascent supernova. In the frenetic month following its discovery, SN 2023 ISF's behavior was meticulously documented. The supernova surged from relative obscurity to dazzling peak brightness within just 5 days, only to embark on a slower decline, dimming by 0.03 magnitudes daily. Spectral analysis revealed a wealth of bright emission lines, a testament to the violent interaction between the expanding supernova shockwave and the gas surrounding the star. This wasn't just a star ending its life. It was a massive star collapsing under its weight as its nuclear fuel was exhausted, with the outer layers rebounding off the dense core in a stunning core collapse supernova. What makes SN 2023 SF particularly intriguing is the dense shell of gas it ejected prior to the explosion, significantly affecting the propagation of the shockwave. Two potential scenarios could explain this dense circumstellar material: Either a strong, steady wind had been shedding material from the star or the star experienced irregular eruptions, ejecting material into space. Either way, it is estimated that the star lost up to a solar mass of material in the last 1 to 2 years of its life, indicating that its final moments were anything but quiet. Identifying the progenitor of SN 2023 ISF has become a focal point of study. Through various methods and datasets, researchers have zeroed in on a likely candidate, a red supergiant. By studying the details of SN 2023 ISF's explosion, including its progenitor's characteristics and the processes leading up to its final blast, astronomers can refine their models of stellar evolution and supernova mechanics. These insights directly inform our understanding of Betelgeuse's current state and its potential path to a supernova, offering a clearer picture of what signs to look for and how to interpret the complex behaviors of massive red stars.